Hi everyone, I am Ferdabati and this is a lecture on linear regression. These are the topics we will be discussing in this lecture. So simple linear regression, which involves only a single predictor, and multiple linear regression, which involves more than one predictor, and then the typical model fitting activities. Once the model is fit, how do you evaluate some of the metrics and the ways to evaluate the performance of the model, the goodness of it, and then we will discuss about some common regression issue that you need to be aware of. So, what is regression? It is a statistical measure of the strengths between a dependent variable and a set of independent variables. Now, throughout this lecture, I may refer to the dependent variable either as a target variable or response variable, and the independent variables as explanatory variables, predictors, or regressors. These terms are synonymous, and people from different domains have a preference to one term over another, but they mean the same thing in general. So, what does a linear regression model? It models the expected value of a numeric quantity. That means the dependent variable or the target variable is a numeric variable, while the explanatory variables can be numeric, categorical, or any combination of the two types. So the independent variables are basically input variables and can take many different values, while the dependent variable changes as a consequence of the changes in the independent variable. And as for the application, regression can be used primarily in two different ways. One is as a prediction, and the focus is on predicting or forecasting a numerical value without necessarily focusing on the underlying relationships between the dependent variable and the independent variables. In another application, which is commonly called advice, what you are interested in is the dependent variable and the relationship between the dependent variable and the independent variables, which is called again commonly advised. And in such application, you are interested in the form of the function or how the predictors are associated or related to the response variable and how strong are the relationships or the nature of the relationship. So in such application, you have interest in understanding the underlying relationship in the functional form. So as I said earlier, in simple regression, we model the relationship between a single predictor and the response. Mathematically, the relationship between the regressor and the response is expressed like this. This equation right here. So the response y is a function of the intercept term, beta 0 here, plus the slope term, beta 1 times the input variable plus the noise or the error term. The intercept beta 0 is the mean value of y when x is 0. Okay, if the domain of x includes 0 and when the input becomes 0, the value of the intercept becomes a value that the response variable takes. Okay. The slope beta 1 is the change in the mean value of y per unit change of the x value. So an important assumption in linear regression in general is the error is uncorrelated and has mean 0. Okay, which means there is no systematic bias in one direction or the other. And the mean value of the error terms are 0. And then we have an unknown constant variance. Okay. Here is how you may be able to explain a simple regression graphically. You have x input variable and y as a response, and this is your regression line. Okay, this is best fit to the data, and this is represents the regressor. So for a unit change in x value, the beta 1 here, of the slope determines the rate at which the response changes. Okay, that's how you explain this graphically. So how do we estimate the parameters, the betas? By far the most common estimation technique in linear regression is least square estimator, which is an optimization technique that minimizes the sum of the square difference between each observation and the value on the regression line. Okay. Although least square is the most common, though, there is another type of estimation technique called maximum likelihood, which, if certain assumptions are made, you can actually use maximum likelihood and still get the same result. So the betas we showed earlier are the population parameters. Here in this equation here, we show them as beta 0 hat and beta 1 hat, since these are estimated quantities using estimator, whatever estimator you employed, like least squares. Again, I may refer the betas as parameters or coefficients. They mean the same thing. So here, the i's response value is equal to beta 0 hat plus beta 1 hat times the i's x value and plus the error value, which is the difference between the point at the regression line and the observed value. Okay. Again, the i's are indices for each observation or point in your data set. So least square regression is about minimizing the residual sum of squares. So here the residual sum of a square is the sum of the error terms, okay, of each observation, which is nothing but the difference between observed value and the estimated value of the response, and we square that difference and sum over all the observation, and we try to minimize that. That is what we do in least square. We try to minimize the total sum of square. So here, when we plug, so the yi is the estimated value, so plugging this equation right here is what you get here. So this is effectively how you implement it. In general, in optimization, so this is an optimization problem, we take the derivative of the function and set it to 0 and solve for it. And when you do that using some calculus, you get this is the underlying equation. So that is how the betas are estimated. Actually, for smaller samples, you can test this manually by plugging the values in your data set. But usually we use software programs like Python or R in real-world application. So after simplifying the algebra, this is what you get. Here, yi is the i's value of the observation for the response, and xi is the x value of the i's observation, and x bar is the sample mean. So the mean that is taken from the data, from your sample. That's the x bar. Similarly, for solving the intercept, the beta 0, you get this equation right here. So, and then this is the beta 0 hat, and which is the difference between the sample mean of the response and the product of the beta 1 hat and the sample mean of the input variable x. Okay. Here is a further explanation of the fit-in model against the population parameters graphically. Probably a bit easier here. As before, x is the input and y is the response variable. X and y here. The green dotted line is the population regression line, which we don't have access to and we don't know it. So we are estimating it because the population parameter, the betas, are unknown to us. But we do know the beta hats. We estimate them using the observation in the sample data. So by employing least square estimator, which is shown here with the purple line, that is the estimator or the feeder line, or effectively the regression model. So as you can see here, the estimated regression line, the blue line, is not quite perfect with the population line, the green line, but very close to close there. So this is a good approximation. Now, one thing that you need to remember is even if you are able to perfectly estimate the regression line, that is, even if when you have an overlapping estimated line on the regression line, so if you have these two lines overlapping on top of each other, even in that scenario, you will still have an error because it's unlikely that all the observations scattered that you see around this line, it's unlikely all falling on the line, right? So in statistical learning of this kind, there are two error terms. In one, by improving the fitted algorithm and through tuning, you can reduce the error, and it's called reducible error. The other one is an irreducible error, regardless of how accurate your model is. There is an inherent bias or inherent error term, and is going to always be there. Okay. So how accurate is our estimation? So regardless of what technique you use for estimating the parameters, how accurate the estimation is also a very important part of linear regression estimation in general. By the way, least square is an unbiased estimator, which means if you take multiple samples from the same domain and fit multiple regression models, and if you take the average of those, they converge to the population regression line. That means the mean of the sample estimated means converge to the population mean. Again, what that means is that if you do the fitting enough times, they converge to the population mean, and that is usually called unbiased estimator. But how accurate is our estimation from a single sample? So you have a sample data, you fit a regression line. How accurate is that estimation? To do that, we commonly use a standard error to assess how far the estimated quantity is to the true unknown value. Okay. Remember our assumption of uncorrelated error for regression, which is an important assumption in general. So with that assumption, the standard error of the intercept is given by this question right here. Here, the population variance is unknown, so it will have to be estimated from the sample data. So the standard error of the intercept is the population mean, the population variance times 1 over n plus sample mean squared over the sum of the square difference between hx and the sample mean. Okay. And the standard term, the standard error for the slope is expressed here as the population variance over the sum of the square difference between the x values and the sample mean. Once again, we need to estimate the population variance since we don't know it. It is estimated here as a residual standard error using RSS. The RSS is a residual sum of square, which we looked at earlier. And here the estimation is not quite an average value because the denominator is n minus 2. N minus 2 here is the number of degrees of freedom. Degrees of freedom is the difference between the number of observation and the number of parameter, which in simple regression there are two, the intercept and the slope. Okay, now the estimated parameters we discussed so far are point estimates. And we need to have some level of confidence in the estimated quantities. And that's done through usually confidence intervals. We use confidence intervals to express how confident that the true value would fall in a given range. The width of the confidence interval is a measure of the overall quality of the regression line, because the larger the variance is, the larger the uncertainty is in the estimated value. A narrow confidence interval, on the other hand, indicates lesser uncertainty. Here, the 95% confident interval for the intercept is plus or minus 2 times the intercept, and for the slope, it is 2 times the standard error of the slope. So what that means is, with repeated sample of the same size, if you take multiple samples from the same domain, 95% of the intervals will contain the true value, which means there is 5% chance that the true value falls outside of the confidence interval. Now let's talk about hypothesis testing. So after we estimate the parameters and put confidence intervals around them, the next step is hypothesis testing, which is used to assess the statistical significance of the estimated parameters. For a hypothesis test, we first need to formulate the null hypothesis, which is a classical approach. You need to formulate both the null hypothesis and alternative hypothesis, and employ some kind of applicable statistic for the hypothesis. And you define a decision rule to reject or not to reject the null hypothesis. A test statistic is basically a function of a random sample. So you can use a random variable and discuss about the distribution and its characteristics, which allow you to work with null and alternative hypothesis. In order to perform a statistical test, we should know the distribution of the test statistic under the null hypothesis. Now, in the setting where you have a normality assumption, which is the case in linear regression, some variants of normal distributions, such as chi-square and student's t-distributions, are appropriate. So here, the null hypothesis is the beta 1 is 0, which means there is no relation between x and y. And the alternative hypothesis is beta 1 is different from 0, which means there is a relation between the x and y. And effectively, to reject the null hypothesis and claim that there's a relationship with some level of confidence, then we need to establish that the beta 1 hat is sufficiently far from 0. That is what we need to establish to reject the null hypothesis. And to measure the number of standard deviation of the beta 1 hat from 0, we compute the test statistic as the ratio between the beta 1 hat and its standard error. An important component of a hypothesis testing is the p-value. So we calculate the test statistic along with the p-value to be able to reject or determine whether the estimated parameters are significant or not. The p-value is defined as the lowest significant level at which the null hypothesis can be rejected. For instance, if you pick a confidence level of 95%, the alpha value will be 0.05. And any p-value less than 0.05 will support the rejection of the null hypothesis, which says no relationship between x and y, which means with smaller p-values, it is unlikely that the relationship you observe is just by mere chance. That means there is actually a significant relationship with that confidence level. Hence, null hypothesis is rejected when the p-value is smaller than the alpha, and it is not rejected when you get higher than 0.05. Again, this is for the percent confidence level. And if you cannot reject the null hypothesis, the relationship is statistically insignificant. Okay, we discussed 0.05, but typical confidence levels are 0.05, 0.01, and 0.1. Those are, usually what are used in statistics. Up to this point, we talked about how we would estimate the parameters using least square, how we put confidence intervals on the estimated parameters, and then how to perform a significant test on the estimated parameters. Here we discuss about model accuracy in a different way, which means how accurate the model is, which is also called goodness of fit. That means on average, how close is the estimated quantity to the population mean, okay? And typically is assessed using two metrics, the residual standard error and the R squared. Now, when you get to multiple regression version of linear regression, we will talk about another variant of the R squared called adjusted R squared, which accounts for the number of predictors in the regression model. Here, we're still talking about simple regression with single predictor. So the regular R squared is relevant here. The residual standard error is the average amount that the response will deviate from the true regression line, which is what we discussed earlier. And you want this to be a small value, right? It tells you how far you are from the regression line on average. So you want that value to be smaller. You want to be close to that regression line, the true regression line. So in a way, it measures lack of fit. The larger it is, the fit is not as good. And it is calculated as shown here in this formula as the square root of the residual sum of a square divided by the degrees of freedom. This is similar to what we discussed earlier. And then, you just plug these parameters into the RSS and calculate for it to find the RSE. Now, although you know that smaller RSE is a good thing in general, it's not quite clear what is acceptable. And that depends on the application, and there's no really any specific value you're after. Okay, depends on the application. Another metric to measure the accuracy of the model is R squared. And unlike the residual standard error, this one measures the proportion of the variance explained by the model, okay? And R squared falls between 0 and 1. Here in this formula, the R squared is calculated as the difference between the total sum of squared and the residual sum of squared, and is normalized by the total sum of squared. The total sum of squared is from a null model. Okay, this is a model by just taking the sample mean. You're not fitting any model, just taking the average. And the RSS is as a result of fitting a model. Okay, so if the two quantities are close to each other, that means the fitted model is not doing any better than the null model, the simple average. And when that happens, the R squared get close to 0. Okay. And if the RSS is much smaller, and the difference between the two is large, and this normalized quantity gets close to 1. And the closer the R squared is to 1, it is an indication that the model is a good model. Okay. That it means it was able to explain most of the variability in the response. And if it's not a good model, that means if the R squared is close to 0, it means it is not any better than the non-model. You can take the average, so it's not worth fitting a model. Now, low R squared could potentially mean two things. One is the actual model is not good. It's not a good fit. Maybe some of the assumptions that are inherent in regressions are not made or violated, like maybe there is nonlinear relationship between the predictor and the response variable, or the errors are correlated. Remember, one of the assumptions is the error terms are uncorrelated. Maybe that's not met. And the other thing could be that you just have too much of a variance to model. Okay, if the variance is too large, it doesn't matter how perfect the model is. That variability, the linear model will not be able to contain that variability. If you remember, there are two types of error: reducible and irreducible error. The reducible error, you can tune the model, perfect your model, and be able to reduce it. But if it is irreducible error, then there's not much you can do. You won't be able to reduce the error by a linear model. What we discussed so far is about simple linear regression, where you have a single regressor and a single response variable. Now let's move to multiple regression, which is nothing but an extension of simple regression concept, in which you have multiple regressors and a response variable. It's basically an extension of the single linear regression in concept and in the way you fit the model, which applies least square. If you remember from simple regression, the population regression line is expressed as here, as the y, the response variable, is beta 0 plus beta 1 times x1 plus the error term. Okay. Now we do have additional terms to account for the additional predictors or regressors. So in multiple regression, we have two or more regressors, okay? Other than that, the form of the function is similar to what we saw in simple linear regression. The beta j interpretation here in multiple regression is a little different from simple linear regression. If you remember earlier in simple regression, the beta one, the slope, is the amount of change in the response variable as a result of a unit change in x, okay, as input, that single input. But in multiple regressions, you have multiple predictors, so you have to control for the additional parameters. To measure just the effect of that variable, you need to control for the others, okay? So what it means is when you look at the j's beta term, it is interpreted as the average effect of y, effects on y for a unit change in the xj's, keeping the other predictors constant, right? So this is one of the benefits of linear regression, in fact, because the change in the response is measured as a result of only one variable and keeping the other constant. The other thing is the representation wise. If you remember from simple regression, the regression line it was a line, right? The fitted model was a regression line. And the way the least square works is it estimates the response by minimizing the error terms between the observed value and a point on the line. Here, in multiple regression, we're dealing with a hyperplane because it's not just a single predictor, so it's not a line anymore. For instance, here in this visualization, we're dealing with two explanatory variables, x1 and x2, and there is the response variable y here. So this is a three-dimensional plane, not a line. So the least square minimizes the difference between any observed point and the closest point on this plane. Now, if you take this into a higher dimension, it becomes difficult to visualize, but the concept still applies. So we apply least square to minimize the observed value and a point on a hyperplane. Okay, so effectively the same formulation, the same kind of estimation interpretation becomes a little different, and then you have more variables to account for in multilinear regression. Again, similar to what we did for simple linear regression, least square is what is commonly used for estimating the parameters. And it does so by minimizing the sum of the square of the difference between the observed value and the fitted hyperplane. Okay. Again, the representation of the fitted model is hyperplane, and that is represented here in this equation. The form of the function involves matrix algebra. This involves matrix algebra. And I won't go over the details of how you do matrix multiplication. It basically involves matrix and vectors algebra. And of course, in practice, we use software packages to do the calculation. We rarely do this. Well, for non-trivial problem, you can't really do this manually. We rely on software packages. So. But if you're interested to understand the underlying math, read any matrix algebra textbook. The relation between the matrix and the vector notation is the key elements. And so, again, just go reference to any matrix algebra to understand that. Important elements multiple regression. So now we're dealing with multiple predictors, so we need to account for are all of the predictors or are some of the predictors are related to the response variable. That becomes important. And also, how do you assess the goodness of fit of the model? Similar to what we did for simple regression, but now you have more predictors to deal with. And for a set of given predicting values, how do you estimate the response variables? Okay. Those are important elements in multiple regression. So just as in the linear regression case, we have to do hypothesis testing here as well for multiple linear regression. We have the same assumption here. The functional form is the same, and the formal test requires that the error terms are independent, which is the same assumption we did for simple linear regression. And they follow a normal distribution with mean zero and constant variance. The null hypothesis is a bit different here, though, from that of simple linear regression. Here, the null hypothesis says that all the predictors have no relationship with the response. That means all the betas are zero. And the alternative says that at least one regressor is related to the response variable. At least there is one beta value that's non-zero. If the null hypothesis is true, that is, if there is no relationship exists, the sum squared due to regression, which is the difference between the TSS and the RSS, which we discussed earlier, follows a chi-square distribution and is independent of the RSS. Okay. And the ratio of the two independent chi-square random variables, each divided by their respective degrees of freedom, that follows an F distribution. Okay, that means we can use F statistic for our hypothesis testing. And the F statistic is expressed right here, which is the difference between the total sum of squares and the residual sum of square divided by the number of predictors, P, over the residual sum of squares divided by the degrees of freedom, which is n minus p minus 1. And if the null hypothesis is true, that is, if there is no relationship the numerator of the f statistic goes to the variance. Okay, if it is true, it becomes the variance. And from our linearity assumption, and if that holds, the denominator becomes a variance as well. So both becomes the same variance, and the same variance over the same the variance will give you 1. So which means if there's no relationship, the statistics becomes. On the other hand, if there is no relationship, if there is a relationship rather, the f statistic will be greater than 1 because the numerator of the f statistics will be larger than the variance. Okay, and in that case, there is a relationship, and we can reject the null hypothesis. So a bit involved than the simple linear regression in terms of hypothesis testing, but effectively the same formulation. Just the manipulation and the terms that are involved with a bit more. Okay, now let's talk about the difference between the test and f-test. Okay, we use t-statistic for testing the significance of the estimated parameters and assess the effect of the J's predictor on the response, controlling for the other predictors. Now, even when there is no true relationship, there is still a small probability of some predictors with very small p-values. If you remember, with a 95% confidence level, there is still a 5% of significance by just chance, right? Which means that the number of predictors goes up, the chance of identifying wrong significance increases. So what the f statistic does is account for the increased number of predictors when testing for significance. And therefore, the f statistic supplements the t-test, and it doesn't suffer with large number of predictors as it accounts for the additional predictors. So what is adjusted R-squared? Remember that R-squared is used to measure the amount of variance explained by the simple linear regression model. In multiple regression setting, we have many predictors, and the R-squared logic is that as the number of predictors increase, that it gets larger, even when some of the variables have weak or no correlation with the response. Which means we need to adjust the R-squared in multiple regression to be an accurate metric, and that is what adjusted R-squared means. If you look at this formulation here, it has a term to account for the number of predictors. It means it only increases if the additional terms truly improve the model performance, and decreases when a predictor improves the model by less than what is expected by chance. It is always less than R-squared, and the two becomes equal if all the predictors are truly correlated with the response. Okay, if all of the variables in the models are truly correlated, then the R-squared is effectively the same as the adjusted R-squared. And adjusted R-squared can also be leveraged for overfitting issues, which we haven't discussed yet, which we will study in subsequent units. Okay, issues in linear regression. There are some important issues to remember. When we started early in this lecture, we talked about some of the assumptions that need to hold in linear regression. So one issue is nonlinearity. That means if there is a strong nonlinear relationship, the model won't be as accurate. Residual plots help identify nonlinear relationship, and we can use some nonlinear transformation that we will look at of the predictors to mitigate such issues. Uh, Another one is correlated error terms. Uh, if you remember, an important assumption of linear regression is the error terms, the E1, E2s up to En, they are uncorrelated. And if they are, then they cause some issue, like the standard errors tend to underestimate. Uh, P-values will be lower, resulting in wrong significance conclusion. So even when there is no relationship, confidence interval would tend to be narrower, and overall it leads to wrong confidence in the model. So that's an important issue as well. Another issue is a non-constant variance of the error terms. So we assume that the error terms have non-constant variance. I mean, constant variance. That means if they are non-constant, then there's an issue. And this is usually called, a common term used is heteroscedasticity. So heteroscedastic is a term explaining non-constant variance, which means the variance increases with the response. The response goes up, the variance goes up. So the validity of the confidence interval, hypothesis testing, and standard errors, they all depend on constant variance. And if you do have a non-constant variance, then you have an issue. And usually a residual plot is used to identify heteroscedasticity. If you look at a funnel shape in the plot, that's an indication of this issue. And you will see it when you fit linear regression model. And also transformation of the response is a way to mitigate it. Okay, another issue is outlier. An outlier is an extreme observation, which means a data point with response value that is much different than the general trend in the data. And outliers typically don't have much effect on the least square fit, but they do have effect on the RSEs and R squares and some of the metrics that we discussed about it. Residual plots, box plot, and scatter plot can be used to identify outliers. I mean, it's just easy to identify outliers. And usually what is considered outlier is not always clear, but in general, like 3 to 4 standard deviation from the mean, they are considered outliers. If we know the outlier is due to data error, then it is safe to remove it. Another issue is high leverage points, which are extreme observation in the predictor values, and they do influence the fit, and they're easier to identify in simple regression, and they requires to compute leverage statistic for multiple linear regression. It's not as easy to identify them in multiple linear regression setting. And last but not least is collinearity, which refers to the presence of correlated predictors. And it presents difficulty in regression context as it is difficult to separate the individual effect of each predictor. And collinearity in general leads to reduction in the accuracy of the parameters estimates. It tends to increase the standard error and reduces the ability to correctly detect an non-zero coefficient. A simple detection method for that is using the correlation matrix, which of course only detects a pairwise correlation. For multicollinearity, we use variance inflation factor. These are things that we will cover when we fit model. Ratio of the variance of the J's, J's beta, the BJ's of the full model and its variance. If the variance inflation factor is larger than one, it's indicating of collinearity. And by the way, you can remove correlated variables in a simple mitigation. So one way to mitigate is if they're correlated, just get rid of it from the model. Okay, lastly, let's discuss about some regression considerations. So regression should be for interpolation and not used for extrapolation. That means you have to use regression within the domain of the predictor values. Okay, that is what you fit the model. If the model has never seen those values, and during scoring or during the application of your regression model, if the x values are outside of the domain, that's extrapolation, and then that's not valid. Don't use it, only for interpolation purposes, not for extrapolation. The relationship in regression are not necessarily causal. Okay, even when you perform significance test, it only indicates that the presence of correlation. It doesn't say anything about causality, so you need to perform additional things to do causal determination. And having large number of variables or categorical variables with large number of levels is a challenge. It is a challenge. They may tend to overfitting issues. Again, we haven't discussed that, but in general, they present challenges when you have very large number of variables. Also, overly large coefficients, if the beta values are overly large, and also large standard errors, and also wrong signs of the estimated predictors or parameters, those are indication of correlated input. That means the predictors are correlated. Model diagnostic on the training data is valid. Yes, so you can have some level of understanding about the model diagnostic based on the training data, but truly have good understanding about the model performance, you have to use the independent test data. That's a good practice, and we will continue to do that in latest machine learning, how do you have a test set to be able to validate and evaluate the model performance. And lastly, lurking variables. Those are not among the explanatory variables, and they can make results to in general, just to the misleading model. They result in a misleading model. So lurking variable, just be aware of those variables that are not in the explanatory variables. Okay, these are some issues, and I think that this the end of the presentation, and we will discuss the rest of the materials and how we use regression for classification setting, logistic regression, and things like that when we fit models. Okay, thank you.